Let's use the integral form for the inverse hyperbolic secant that we just derived. We showed that the integral of du over u times the square root of a squared minus u squared equals negative 1 over a inverse hyperbolic secant of the absolute value of u divided by a plus a constant, or in the log form, negative 1 over a natural log of a plus the square root of a squared minus u squared divided by the absolute value of u plus a constant. Now, when we make any effort to use these forms, what we want to do is first recognize that if we have a square root and what appears to be a u, this is probably a good place to start. So when you look at this indefinite integral, we have a 3x minus a 6. Again, you can factor the 3, which I've done here, to give a 1/3 times the x minus 2. Now, that would be a good candidate for the u. So what I want to do is make an effort to complete the square to see if I can produce the u squared. So now, of course, this particular quadratic has a leading coefficient of -1. So we'll go ahead and factor to make it monic. So we're going to get an x squared minus a 4x. Now, half of the -4 is -2. Square it, we get 4. So let's go ahead and add and subtract 4. And notice now x squared minus 4x plus 4 is a perfect square. It's x minus 2 quantity squared. So now when we distribute the negative, we get the negative of x minus 2 quantity squared. And then negative here gives us a 4 plus a 6, or a 10. So now as we move to the next line, we have 1/3 times the integral dx. So we have x minus 2, then we have 10 minus x minus 2 quantity squared raised to the 1/2 power. And notice here I've just used the 1/2 instead of writing the radical sign just to save a little space. Now we can see that we've completely matched this. Notice the chain rule just says that all we need is a dx, so this is basically table ready. And one thing that's nice about it is that not only do we have the u, but we have the a, which is the square root of 10. So everything's ready to go. So let's go ahead and use all of our forms just to get practice with that. So of course we have the 1/3, which comes along from our initial factoring. And so we have -1 over a, which is -1 over the square root of 10, inverse hyperbolic secant, absolute value of u, which is absolute value of x minus 2, divided by the square root of 10 plus a constant. And now, of course, let's go ahead and use the log form. So that'll give us the -1 over 3 root 10. I just push these two together. So we have the natural log of a, square root of 10, plus, and now, of course, a squared minus u squared is just the original quadratic, so you can just go ahead and write the square root of -x squared plus 4x plus 6 if you like, either way, divided by the absolute value of u, x minus 2, plus a constant. And now, of course, I haven't mentioned this, but this is also true for the inverse secant function and the inverse cosine function in the regular trig functions. We have this identity that is the inverse hyperbolic secant of x equals the inverse hyperbolic cosine of 1 over x, basically using the fact of how we've set up these functions. So when x is in the interval 0 to 1, the reciprocal is in the interval 1 to infinity. So this is going to make that particular identity work. And so if you like, if you just want to bypass the log form altogether, you can rewrite this antiderivative using the inverse hyperbolic cosine. So you'll get -1 over 3 root 10 times the inverse hyperbolic cosine of square root of 10 divided by the absolute value of x minus 2 plus a constant. So basically you reciprocate the argument. But that's really neither here nor there. Basically what I'm showing you is that as you learn more techniques of integration, there are many, many ways to write antiderivatives. And it will not always be clear that certain antiderivatives are equivalent. Remember from the mean value theorem, functions possessing the same derivative differ by a constant. But that may be very difficult to show, especially when you're working with inverse hyperbolic functions, logarithmic functions, and trig functions. So we're done.